I can be open. Okay. Anyone who wasn't here before the break? Yep. I can do a quick refresh, just to get everyone like a 2-minute, 3-minute refresh of things. Can be good for everyone because I had to go through something really quick in 30 minutes there. Let's see if I got everything here. Right, so this lab right here is about maximizing then, CPU core utilization. You want to use the cores that you have, and how do you do that with NSO and transactions and updating devices. That's what the previous presentation was about, and also how we can avoid it. But this here, we want to do it. We want to not stay on a single core. We want to spread things out on multiple cores. And when we talk about transactions, this is the transaction then in blue here. The service update is what happens first after the read-write. This read-write here, after that phase was done, on the left here. Previously with NSO 5, then you had a lock taken there. Now the lock with NSO 6 is moved to after the validate phase, the green phase there. And it's let go when the devices have been updated or the commit queue has been updated, had you turned on the commit queue. NSO 6 checks for conflicts. So what you want to do is design if you want to run things concurrently, you want to design your service so that one service instance does not update things that the next service instance that's running concurrently is also doing. Is also making changes. So if one service instance reads, for example, some lists, and this other service instance have updated that list, that's a conflict. So the one that gets here first take the lock, go through and continue. The other one will have be flagged for a conflict, and then depending on how you set it up, you can set it up so that there's a retry down automatically. There can be a retry that calls a callback that you defined, or there can be that you say, okay, I want to abort the transaction if it conflicts with another transaction. So I won't go through the conflict handling here, but there's text in the concurrency model chapter in the development guide that explains this in detail, and also there's an example in this example set where all the other examples we're using for this lab is. Let's see what else. Yeah, you will see this progress trace visualization here that I used in the presentation before. That this is very useful to see. Okay, what is actually happening? Am I achieving the concurrency that I want? If not, then that will show up here. So this was just one transaction, but this was without commit queues. Let's see. Yeah, so something like this is what we want to see. We have 2 transactions here running in parallel: service create, validate phase, and then deploying to the commit queues, and the commit queues doing their thing. That happens in parallel too. So why do we need commit queues? Yes, because if we have several transactions, if we don't use commit queues, one transaction have to wait for another one to update the device if we don't use commit queues, and that can take some time. So to be able to parallelize several transactions deploying to devices, we need commit queues. So if we've done all this work here, we do this concurrently, create phase, validate phase. If we don't have commit queues, the point is kind of, if this is a significant time, it's a very short time, it doesn't matter. But if this is significant time, most of the time it is. Most of the time it takes longer to update the device than it takes to go through these phases here. But that can differ, of course. But so if you want to minimize the time it takes to the throughput then of these transactions, all these tools need to be put in place to just get the maximum benefit of your CPU cores and the parallelism in the multiprocessor and in NSO then. Yes. Okay, so I can go through the lab real quick. First steps here, show you some things. But if you have questions now or later, just ask me questions. So this lab right here is based on the examples that we put into the example set quite recently, beginning in the fall, and then we added to that example set. And right now, this is our current examples for showing you how to do these things of making things concurrent and so forth. There's if you clone this repository, you need of course NSO installed. 6.2 something would be good. Latest 6.2 has the best performance, and so does 6.3. So if you get any of those, that's fine. 6.1 works as well. 6.0 works also. So it has the same functionality, basically all the functionality we need. But if you don't have NSO and don't want to install it, there's as you may have seen, this Visual Studio kind of setup where you get NSO. You can log in with something like GitHub or your Cisco ID if you have one. You can register for one. You don't have to. You can use any of those login methods. And then you get it set up right here, which is basically a 2-core CPU. This is, of course, a VM running multiple instances of this for all types of users. So this is quite unreliable, as you will see if you run these examples in this setup right here. But you will, it works. You can test it using this setup here, so you don't have to have NSO installed. You just run it here in the Visual Studio NSO setup, and you will have 6.2.1 here. There were some improvements to 6.2.5, and we'll update this to 6.2.5 and then to 6.3 at a later time too, quite soon, probably next week to 6.2.5 because it came out this week. And there's some performance improvements, especially when it comes to what I showed regarding MAPI set values, MAPI create, MAPI set, and so forth. For example, when you have a bunch of things being generated by the service, and there needs to be service metadata, that process was improved in 6.5, and you will notice that if you go through the performance set values example. So the example set. Let's see. Yeah, it's all red because I put in PEP for 8 for Python, and it's complaining, so we need to fix those things. There's a ticket on that to make the styling according to what it's supposed to be. Well, anyway, in the example set, there's if you've seen that, there's the development guide folder, and then you have the concurrency model. Here you have the examples that this lab uses. The set vals was the one I was talking about that's recently added, so that's not in 6.2.1, so it came in a tarball in the lab, as you may have seen there. So what came first was the performance transaction example, which you can do multiple things with. And then the zone-based firewall, which we don't use in this lab, but you can check it out. It basically has a very complex setup of updating through templates and Java code and so forth. Performance stack, that's the one that uses a Nano service and the CFS. And the performance LSA is the one that uses then the LSA setup that I showed in a picture, where you can scale infinitely if you actually utilized everything you could in your system, and you want to go to the more complex setup of having an LSA setup, then yes, there's an example here for that. In the common folder is what I pointed out, the small Python script, which does a small part of what the observability exporter does, but it's very useful for this kind of work that we're doing here, where we have this progress trace. All right. So if we go back to the lab here. So we recognize the pictures. I reused some of the pictures I had for the presentation in this lab here. So this describes first how to run the performance transaction example. And the performance transaction example, we can begin there. In this lab out here, we begin by testing, okay, what if we don't care about parallelism here and concurrency? We start a single transaction. It will do some work for 2 seconds, simulated work, simulated validation for 2 seconds, and then update the device without using commit queues with a commit queue bypass. So if we run that, it will look something like this. I have a cheat sheet because I didn't script this. All right, let's see. All right, let's just build it. Create 10 NetSim devices, simulated devices here. Okay. And here we're doing actually 3 devices, right? Was that what I put in here? Yeah, 3 devices with 3 seconds of work each, basically a Fibonacci count. If we look in the packages for the service create code, which is then Python code, and there's no template used, so it's a straight Python code maps to the device. And so, yeah, so that took 756 seconds, and we can use this simple progress trace visualization. We have this single transaction that does this create, the validate, and then deploys, a small, tiny configuration to the devices, but this is done in parallel. So if we use one transaction, and then it makes no sense to use a commit queue. You don't have to use that unless you have some special reason for it. There's other reasons for using commit queues, like, okay, the device might be down, so you place it in a commit queue, and then you run the commit queue to populate the device when it actually comes up or something like that. But that's not what we're talking about here. Here we want to get the configuration out to devices that are actually up and running. So, well, if you have one transaction that updates several devices, 3 devices, for example, then the push of the configuration is done in parallel. So then we don't need a commit queue to do that from one device to 3 devices. It's just one transaction, so no commit queue. Commit queues, remember, are good for if you have several transactions running concurrently. They cannot update the devices concurrently unless we use commit queues. So that's why we have that. So then to tweak this example, we can then have one transaction per device, which then becomes one transaction per CPU core. I have 10 on this one, this MacBook here. So I just reset the example just to get a clean, fresh slate to be able to compare, to not have anything already set in CDB and so forth, so we can compare the time it takes. So this example just calibrates the CPU, the Fibonacci counting sequence, or Fibonacci counting to be close, so that we can use it to control how many seconds we want to simulate work in the create phase. Now, if you don't want simulated work, you can look at the performance zone-based firewall example or the performance set values example. That is real work that actually done, not just simulated. But here it's kind of nice to have simulated work just to be able to compare. Is the parallelism working here as we should? So you can see how much this took, about half as much time to do 3 devices. In the lab instructions, it's for 2 devices, and that's because of the limitation with the playground that I talked about. So if you're using the playground, you only have 2 CPU cores, so that's why I tailored it for that. But you can increase the number if you want to do that. Okay, I showed you the conflicts with. So this will take you back to NSO5 dark days where they had the transaction lock right after the read-write. You find the minimum diff and then you take the lock, and then everything done in the create callback and in the validation phase is done then inside the critical section. So we can kind of simulate that by setting this conflicts with setting. So if you look on the packages service, let's look at the package repository as we called it here. You have a Java variant and a Python variant in this example. I'm using the Python variant here but they have the same Young model. So this Young model this is like something, okay, we uncomment this if we want things to be serialized then, the way I described it. So then to detect if you want to see something done in parallel in the trace log, here you have all the 3 services, or the 3 transactions, different colors because they have different trace IDs. That's how we separate them. And you see the service create, you see the validation phase, and then the push through the commit queues. Now if you turn on the conflicts with flag, I still start 10 devices, but I'm just using 3 of them. So calibrating the CPU time again, just doing a fresh start, empty CDB and so forth, just to get the same comparable result. Doing restconf patch transactions. So I'm using the Python multi-processing library to spawn then 3 restconf transactions using Python request from a Python script, just to get them in at the same time to NSO, so that we see what happens. That's what's done there. But now you can see that, okay, since I turned on that flag so that they now run sequentially, as you can see here, the create, validate, start holding transaction lock, and push the configuration. That's done one device after another. This would be bad if you wanted concurrency. This is non-concurrent. This is sequential. So look for that. Yes. Okay, so then in the performance transaction example that we use now, you have a README that also you can check out if you want some more details than what's in the lab. I took these and put them into lab, the ASCII sequential charts that show you what's going on for each of these tests that you do. If you want to dive in then to what's actually going on inside here, and what's being done, then you would look at, let's see. Right, okay, we didn't write that in the README here, but anyway, what is used, as you saw, is this measure script, which is basically setting up progress trace. You may wonder, by the way, why there's a transaction down here that takes almost no time. This is turning off the progress trace, is what we do in this. So I didn't make this, or we didn't make this Python script take away the last transaction that actually is transaction that says to NSO turn off the progress trace. So it will be included in the progress trace. So don't be alarmed by this last transaction right here. All right, so this one here runs either a test, which is then spawning all these processes to run restconf patch transactions towards NSO's northbound interface. And that's what it's doing. It can also run a single transaction And then what it does is just using the progress trace to well, it prints the time it took, and then just uses the progress trace to get the output that you saw. So it's really hard to read that progress trace in its CSV format. So the benefit of the observability exporter, which is a whole suite of tools, plugs into Visual Studio, and then you also have this simple little Python script in the common library, common folder there also. You could see the benefit, right? So, I mean, it's quite helpful to, instead of reading a comma-separate value file with different trace IDs, get coloring on the trace IDs, understand which transaction is which, and just see, okay, in which order does this happen? So that serves our purpose here. That's a really good way of figuring out, okay, am I achieving some parallelism? Concurrency. Yes, so you can run this lab. You can ask me questions. That's what I was thinking. Did I forget to show something? Yes.
So for the trace exporting and showing it as a table, do we have something similar to export this to, for example, Grafana or another tool?
Yeah. Yeah, like this observability exporter I talked about, that utilizes all of those things. Yes. So. Okay. I didn't know that. Yeah. Right. And then there you can do much more stuff with this progress trace and with many other things as well, to check the state of NSO and get some metrics and these kind of things. So yeah, I think that should be another lab that we should have to use the observability exporter. But it's good to know at least that, you know, even this simple CLI-based just output of the CSV, the comma-separate progress trace, so much easier just to use this. This is like 50, 70 lines of Python, and it's super simple. Helps so much. Yes, anything else on the performance transaction example that, or anything in general that you're wondering about? Yes.
You mentioned that you used Partner Fast to request services. If you in Yang patch, you can actually bundle requests, and that assumes the same. Or would that be one isolated transaction?
Yeah, Yang patch would be one transaction, right? One Yang patch.
Spans different services with different devices.
Yeah, it would be one transaction, even if it spans several services. Yes. Yeah. Yeah. So.
And regarding logs, it would be the slowest device of one's reference that would be finding the log.
Yeah. Yeah. So if you have one transaction, NSO will still parallelize everything that goes out to devices. So then, yes, the slowest device will then determine how long the actual critical section will be, where the lock is taken.
Yes.
Yeah.
You have a slow CLI device which does
Yeah.
not play well with commit queues.
Yeah.
Kind of lost.
Yeah. Yeah. Then you're going to use one CPU core, so all the things that have been done before the lock is taken is going to be sequential, and then okay, you get some parallelism in the end, but the slowest device will dictate how long that lock is taken. So if you have another transaction coming in, then that will have to wait for that or fail. Yeah.
But a layer service setup would improve.
Well, thank you for mentioning layered service setup. Well, yes, it will improve things, but it comes with a cost, the layer service setup, not in performance. It solves performance problems, but it comes with a cost of complexity, of course, because now you have several instances of NSO managed by one CFS upper NSO, and then 1, 2, 3, 4 additional NSO, or maybe you want HA also. Probably you do. So now you have an HA setup for all these different NSO nodes. So what you want to do is like I described. Okay, you want to explore all possible avenues of optimization with this one node NSO. That would be definitely recommended before, not too easily jumping to LSA. You want to find the bottlenecks, try to optimize the bottlenecks, of course, making sure that you're using all cores. Makes no sense to have a 100-core multiprocessor and then have 10 of those and just use one core on each for even an LSA setup, right? Or 5 out of 100. So you want to maximize the use of that before going to the LSA complexity, right? So if you have a multi-core processor, maybe you want to change that multi-core processor to something that has more cores to avoid the complexity of LSA. Maybe that's less complex actually to do that change. I don't know. Depends on the what's possible and not. Faster clock speed, all these things. Right. So you want to verify that. So yeah, this is what the other guys who actually developed these features here tell me that, hey, if you want to show LSA to people, you got to have this disclaimer because it will come with a cost, and you need to know the cost is complexity, and that others before you that have gone to that complexity for different reasons, some changed their mind and some are very happy that they did that because they actually had done all of this, or they had some other use cases where they needed more memory or something like that, and going to LSA solved something, or they had thousands and thousands of devices and they needed to update those. So to be able to do that, LSA made sense or something like that. So yeah. Right. Back to the performance transaction example, or anything other. We can jump back and forth like this. That's okay. Any other questions right now? Yes. So the next one in this lab, the next example, if I may go there, is this performance set values example. So this was a user who created a lot of routes and rules in one go in their service. It's sort of a day zero config or something like that. I believe it was. So they set up all these thousands of rules and thousands of routes in a firewall, basically. If you have such a thing, that it doesn't have to be a firewall, but in this case we're using a Cisco ASA and NetSim device. So if you have something like that, it makes perfect sense to do of setting those to minimize then the service create time. It makes good sense to use bulk updates like you can with MAPI set values, shared set values, and just using create and set for each list instance, for example, of rules and routes. So what would that look like? Back to the cheat sheet. So let's run this example. You can run it with shared create, shared set element. It uses magic, so you don't really see that it's shared something. You just see a create, and then you see, if you look into the code, something being set. You can go back to that. Right, have to actually go to the example. Let me go back and stop the other. I forgot to do that. All right, so you can just run the example like this if you like, or you can run it look into the code or the script that's actually used to run this. Here it's 3,000 rules and routes. We didn't write the routes, but it's 3,000 rules and routes. So you can see that the service create here takes about half, a little bit more than half of the time this transaction actually takes, because we have a short validation phase, but then we have a longer service create phase here. Here we're actually writing data and we're not simulating anything. Of course, we simulate the device, but we're not simulating the work that's done in the service create. That's actually setting Cisco ASA firewall and routes and rules for the firewall. Okay, this was not a valid. It was a saving reverse diff set and applying changes. This is you can do even more. So here you didn't see these things here. We increased the level of output from the progress trace for this progress trace here to be able to separate the create from saving diff set and applying changes. So the diff set part here, which takes some time. Why it takes time is we're doing this from a service, the create and the set, and it's setting some metadata to be able to keep track of, okay, what has this service done? So that's the time that's spent here. And here the create and so forth to the device, the mapping to the device config is done. So that's what's taking time there. We're doing this with, again, the last transaction here is just turning off the progress trace. Why this takes no time is because we do this with no networking. Why are we doing that? Well, the Cisco ASI and NetSim is super slow. So it's using this Cisco iOS set one thing after another with where each creation of something is one transaction basically. An ASA in real life, you can utilize, so you don't have to set everything with one transaction per setting each, or for example creating each rule with one transaction or something like that. So therefore it makes no sense to, this would take with 3,000 on my laptop here, it would be something like 50 seconds or something to, if you do this in the Visual Studio Code thing online, this will take, you can go grab some coffee when updating the ASA. So we do this with no networking here, but still we want to show the point here of comparing between using set values and using create or set element.
How would that compare to a loop in a template?
Yeah, a template would behave and take approximately as much time as create and set element. Sorry?
Not looping over a template, but have a template
Yeah.
that loops over some X path.
Yeah.
That would be the same as the create.
It would take about the same time as the create and the set element in from what I see with this example right here. We were thinking about putting in a template as a comparison here, but we may not have done that. I can't remember the reason for why we didn't do it. I guess it depends on the use case. I would say that if you can use shared set values to do bulk updates like we have here, the bulk update will be bunches of rules and routes in lists. In this case, we set it to 3,000. Yeah, as you can see, like if I run this now, the previous took, yeah, we can check these. These are about 4-5 seconds. Of course, as we increase the number of rules and routes, that number will increase as well. But we don't want to sit here and wait too long, so a few seconds is enough to show the difference. Yeah, so okay. was too fast. The NSO was still writing to the progress trace when I ran the Python thing right after here. Let's see. If we can get the final result right here. Yeah. So instead of this being 3.5 seconds, okay, now I ran two, it doesn't matter. Okay, I ran 2 transactions at the same time. That's doing set values, but it doesn't matter. You can see how they're running on different cores anyway. But this one now takes 1 second instead of 3.5 seconds. And this one takes 1 second instead of 1.2, so not much difference for setting the metadata and back pointers for the service. But this is where the big gain is when you're using set values, then 3 times faster. You may want that. If this were like the user of NSO had in this case, it was not just 3,000, it was like 30,000 or something like that. And so then 10x this, and that was significant time for them. So if this phase here takes significant time for you, consider set values is this part of the lab and the lesson.
What about copy? If it's a very dynamic table, you can have it stored somewhere and copy it with one API call.
Like if you can, in your service create, if you can do all sorts of changes and all over the place instead of just a simple list or something. In this case, it's 2 lists.
You have the representation, the same representation as you have in the device. You create that somewhere else in your tree as backup data, and you just copy from there.
Yeah. Yeah, absolutely. Yeah. Yeah, there's ways of getting things to be done fast. The focus here for us in this lab is, okay, you're doing something in the service create and you want to minimize the service create time. So how do you do that? Well,
Traditionally, rewriting everything to Erlang is much faster.
you're hardcore then if you rewrite it to Erlang, but yes, you can do that. This example only has Python, so I don't think we put in a Java. Yeah, this example also has a Java variant, but yeah, next should be an Erlang variant to show you that one, yes.
But I can't find any concurrency in there. I mean, there's one gen server that handles the callback.
Right, you're running, if you run, you can run, of course, inside of NSO's Erlang VM, and
One gen server process.
yeah,
It's the callbacks you need to return
yeah,
the result.
yes. Right. Yeah, I mean, if you're in the service create, then yes, that's one process for that service create. You can, of course, in your service create split so that you then run multiple processes. You know, you can do that in Erlang, Java, Python, and do something in parallel there if you want to. I mean, that's possible to do. But that's, you know, out of scope for this lab right here, I think. It depends so much on, okay, what is your service create actually doing? The use case I want to show here is okay, you actually want to update some configuration in the device, and you're doing that mapping. You're using templates, it's slow. You're using set and create. It's not going so well. Well, set values might then be a good option for you to speed up the mapping to the device. If it's a big configuration, like in this case, or large configuration, like in this case with rules and routes. Yeah, let's see. To the example. So this example too, you can check out the README for more kind of details of things and examples of how you can compare between running just one transaction, and you can also run several transactions with this example to kind of use it similar to as the performance transaction example, and test out running on multiple cores and doing, like you saw in this this progress trace I showed you were about 2 transactions running actually. Yeah, and it will direct you to, you can run the showcase script here, which is basically multiple CLI commits, or you can run this restconf Python request where multiple restconf patches are done, basically. I think it might be, yeah, it's a Yang patch that actually used in this example, and not patches, plain patches. Yeah. And the packages, you have a package repository, so then you have, let's see. Yeah, so you can set this example to either use Java or XML, and Java is nice because it has this API. Where in this example, we just, in the service create, we just generate some configuration. You might have like the user that inspired this example had a file with XML that they loaded into the service create and then set it to the device. They did some manipulations on that file once it was loaded. Here, this example, to not have to have files and to be able to configure like, how many rules and routes do you want? We generate them from the source create. But this takes time, but it takes insignificant time to generate that XML. So then this uses the shared set values, which in the Java API takes XML then, which is far easier to take than conft CDB's internal kind of representation of tag values, which you can generate if you like to do that. But I would stick to simplicity with XML. So XML is the other option to generate if you want to use set values, or take from a file or something like that. So there's plans for doing it, but this does not exist in Python. If you look at the Python variant for multi-set values, here you can get an idea. Let's see. Yeah, so in this case we generate XML as well, but this one takes, at this time it only takes the CDB representation, the tag value thing. So we need to traverse the schema to get the tags that we want to put on the values from this XML that we input. So what we did, until the XML variant of multi-set values is available with the Python API, you can just look at this. This will recursively traverse the schema and take the XML and make it into conft tag value format, and then input it into the set values. Yeah, so this XML here is it's a list of routes, and then it's a list of rules. So then, as input to this measure shell script, you remember here, as input to that, we had, sorry about this. You can select, okay, how many of these rules and routes do I want? So in this case, if I say 3,000, this will tell this, this will be put into the service, a leaf there that says, okay, you should generate 3,000 rules and routes for this example. And so this is now example details. It's not like, okay. So then that value is read by the service create from the service, the 3,000, then we generate the rules and routes in XML format, put it into this grinder that makes it into in this case for Python, since we can't put XML into the set values, it just traverses then the schema and puts the tags on these and creates the conf tag values, and then runs the set values. Yeah, that was a long explanation to a simple question. So thank you. Yeah. So any other questions on the set values kind of thing? All right, we'll move on. So this lab right here, it put in some recommendations also. Like, there's no example for this, but use data kicker instead of CDB subscriber. Why would you do that? Well, okay, so you want to know if something happens with the configuration, and you want to do something based on that. Let's say you want to do that. If you use a CDB subscriber, you will, when you handle that event, you will be inside the critical section. So if you don't want that, if you don't want to be inside the critical section, it's better to use a data kicker instead, if you have a need for doing something like that. If you don't bother about this, don't do it. But know that the data kicker is outside the lock and the CDB subscriber is inside the lock.
Data kick is also after you can't do the same stuff.
Sorry?
Data kick is also after, it's at a different stage. It is committed out when you get the data kick.
Yeah, so you're asking where in this transaction would this happen?
Yes, after the commit.
Yes.
You want to do something with the...
Yes, it's well, actually you have a two-phase subscriber that you can do, and you can have a kicker and so forth. That actually in the prepare phase before the commit, you can get an event. So if you want to do something there, I mean, this was super useful if you're using confd, and in NSO, well, in confd you would have it. Let's say you have a device like the Cisco ASA. If something happens in the configuration, you want to react to that and implement that configuration in the device itself. So yeah, then it makes sense. With NSO, well, if you want to react to something and you have something you want to update when some configuration changes, you can use a subscriber or kicker. But know that the subscriber can, of course, be updated here. This is still inside the critical section, or here after the commit has taken place. Everything is done. If you're doing a two-phase commit, yes, you can abort the transaction from such a subscriber. That's the benefit of that one. Yeah, but it's not that many use cases with NSO where you would need that functionality. But if you use it, know that you're inside the lock and minimize the time you spend in it. All right, so yes, of course, IP over AVN carriers will delay the transmission of the configuration to the devices, and RESTconf and netconf is probably faster, that's true. Yes, let's see where we are. Yeah, so let's look at commit queues. So this lab right here goes through the kind of details of commit queues, which I already, and the benefit of them and why they're useful, which I already explained in the presentation before the break and now. To run it, we can run without commit queues. We're going back now to the performance transaction example. So we left it earlier, now we're back. And now we want to talk about commit queues, and you can run. I already ran this, so you already saw the results, basically. But I can run it one more time. Just let's see how to go back to the example. Yeah. So we do a few RESTconf requests. We don't have a commit queue. And when we're done, we of course see that the commit queues weren't in place. So the devices, since they were done, the updates of the devices were done in different transactions, which meant that they had to wait for each other since we didn't use commit queues. Again, if we use one transaction, the deployment to the everything would be done on one core, but the deployment to the devices would be done in parallel or concurrently, I should say. And of course, if we reset that example and run the same thing with commit queues, we'll get then that output that we saw earlier with the commit queues, making sure that the transactions can write to the devices in concurrently. Anything on commit queues? Anyone has? Or examples themselves, or something that we talked about previously that came up now? Or yes. Yeah. Yeah. Right.
Then we expand our system to LSA. As a rule of thumb, one LSA can carry on like 20,000 devices.
Right.
As a rule of thumb.
If there is a sorry, if there's a limit to that, or what was the question?
So there is no limit. As a rule of thumb, each LSA can carry on 20,000 devices.
Right.
Downstairs, I was talking to someone and he told me that there's going to be a considerable improvement for memory management.
Yes.
So memory is not going to be a bottleneck.
Unless you have very little memory, yeah.
So in this case, by carefully architecting this throughput parameters and transactions, do you think that, as a rule of thumb, the number of devices which can be managed per instance of RFS can be increased, or to what extent can it be increased?
Yeah, I mean, in theory, you can manage as many devices you want from a single RFS, right? What we're trying to show here in this lab is like, okay, if you want the maximum throughput, you want to use LSA for achieving maximum throughput, then you probably, if you can, you probably want to stick with one device per transaction, which means one transaction per core. So you have a core for each device that's attached to that RFS. So if you have like this MacBook with 10 cores available, you probably want something like 8, 9, 10 devices on that if this is the RFS multi-core processor that I'm using here. Or you have a 100-core processor, which we have back in the lab in our offices here, which is nice. But yeah, you probably have something like that. Because if you can utilize cores so that you're not just running one core, by doing these things that we're talking about here, it makes sense then to make sure that you have as many cores as possible available. So I mean, at the very least, maybe you don't have to go to LSA, or if you go to LSA, maybe you don't need 20 RFSs. Maybe you just need 2 or something, because you had so many cores available. So and maybe the transaction throughput is enough, even if you have 20 devices and 10 cores. Maybe that improvement is enough. So maybe you don't have to bother about having one core per CPU. Of course, that will just mean that, okay, it will take a bit longer because you kind of hit the ceiling of the CPU power that you have in that multi-core processor, but that may be fine, so.
Can you say something as a rule of thumb? Number of devices which can be managed per LSO?
Yeah, I mean, like I said, there's like no rule of thumb. It's totally up to how much time do you want it to take? Yeah. And how much resources do you have available? Can it handle it? I mean, you can, if you do anything sequential and you don't care about, that takes a long time, then you can update 50,000 devices with NSO if you have the memory. So yeah, it just takes a long time. But if you want to go as fast as possible, yes, then you may want to dedicate a core per device, for example. You don't need 2 cores per device because that.
One other question. Did we have access to the code that you have shown us? I think
Yes.
NSO.
So yes, all the code is kind of bundled up in NSO. So the only thing I have here, because this was based on the 6.2.1 version here, if you want to run it like the online version, that didn't have this example here. But from 6.2, 6.2.2, I think, and 6.3, of course, also, you have all these examples in the example set. So if you go into if you install NSO with a local install or something, under examples, NCS, concurrency model, there you have all these examples that we're going through here. So you have all the code, yes.
The example with the distribution.
Yeah, so the performance LSA is the LSA example, for example.
Sorry, is this performance LSA is in the distribution?
It's the example set that comes with NSO, yes. Right. Yeah, speaking of LSA, I think are we there? Well, we have this stack example here. This is where we start using a nano service to simplify basically, and then in the end enable for LSA if we want that. But we can use it purely to just simplify. So the performance stack example, the difference there is that previously we had to have all these transactions from the CLI with the multiple commits that is on the performance set values example. We have RESTconf generated by the performance transaction example. You can do that with the set values example too, I think. No, I didn't do that. Yes, you can use RESTconf there as well. But you have to generate multiple transactions, and maybe you have some bit dumber node up here that don't know how to generate all these transactions. So you can simplify for that node by presenting a nano service, so that instead of multiple transactions, the nano service will split this up into multiple transactions for you, for that one transaction. And you can have a very simple nano service to do that. All you basically need is the init and ready state, while the example has a validate configure state. You don't really need to have these different states. You can do your create callback to the Python code or Java code. You can do that from for example, the init state if you like to do that. Okay, maybe we can run that. Stop me if you have questions. So that's the performance stack example. Okay, so this works basically as the performance transaction example. It simulates the CPU time with Fibonacci count numbers if we were to do a sleep, that wouldn't really be hogging the CPU. So we need to do something. So in this example, instead of having these set values or doing some service mapping, we just simulate how long it takes to be able to compare, to get the exact kind of timing there. So now this you can see how this changes the progress trace. You will get the trace ID for the initial transaction. That's one transaction, but then the normal service will start running several transactions, per 4 here, one per device, and do a redeploy, which will then go through and there will be 4 transactions created in the end. You see the different colors we get down here, and they are running concurrently, all of them. And so now we have the concurrency, even though we just had one transaction going in, and the normal service splits this up into several transactions, which the trace ID will tell you that this is a separate transaction, and that has a different color, so therefore the colors here, like I mentioned before. Yeah, we turn on commit queues because, again, I mean, if we have several transactions, they can't commit to the device unless in concurrently unless we use commit queues. So we still have to have commit queues here, since there are several transactions manipulating each one device. So to do that concurrently, we use commit queues.
To have smaller rollback domains.
Sorry?
To have smaller rollback domains if one fails.
Yeah. Yes, if one fails, then the commit queue, if you have the rollback on error turned on, then yes, it will roll it back. And if something fails, then the nano-service transaction fails, and the nano-service will backtrack, which means that it will undo the configuration for the other devices, which means that it will roll back those configurations as well that is set through those commit queues. Right. That was related to your previous question. Right? Okay, again, same thing with this example. It has much more details in the README. You can check that out. This one also has a shell script kind of demo that you can run. And in the lab, you have some suggestions for input parameters to the script. You also have one that uses Python that then uses RESTconf and through Python request it will just set up the progress trace and do one transaction to the non-service. Basically, that splits it up. So it's nothing special with this test code. It's just a few lines to configure the service to say, okay, we want to do this much work. We want to have this many transactions to this many devices and so forth. So that's how it works. And you can see the packages, like with the other examples in the package repository, but now we have in this example, we have a CFS. You don't really need a CFS, but we use a CFS in this example right here to simplify the input, really. So that it's not a list, it's actually just a container, the service, where you say, okay, I want this many transactions, this much work to be done in the validate and commit phase, and this many devices that the transactions go to, and then some ID. That's basically it. And then you set, okay, how long do I want to delay these nets in devices? How long do I want to simulate that work is being done on the device? So this is all simulated as opposed to the set values example and so forth. That actually does some work. But again, it becomes easy to compare like different variants of what you're doing if you simulate the work. That's why we simulated it, so we can control better. And the actual simulation in this case is done in Python. On the RFS, of course. And so the RFS is a list, the service. Yeah, just as with the performance transaction. Yeah, and the simulated work you can see here, the Fibonacci, the CPU hogging that is done here. The factorials, that's what I should say. Not Fibonacci, I meant factorials. Erase that. Sorry. Okay, any questions on this example right here? Yes, let's check the time. Where are we? Yeah, we are overtime right now, according to this schedule right here. So I won't go through the LSA setup, but if you have any questions on the LSA setup, we can take them now. Am I right, Fabrizio, that we're out of time, basically? Yep. I don't want to miss anything that goes on downstairs. So, but feel free to go through this, and if you have additional questions, just you know, I think I have my email, but well, you can contact me or you can contact my colleagues, and we'll help you with that. I'm here tomorrow, of course, also. So let me know if there's something that concerns you at night when you go to bed and you're thinking multi-core. Yep, and transactions and performance related to this kind of thing or anything else, and we'll help you out. And if you find anything that's suspect or something that isn't behaving as it should with examples, just let us know too. That would be great. All right, thank you guys.